Which of the following cations is the most stable? So if we're looking at stability of cations, we want to look at the type of carbon that it's on and say if it is a primary or secondary or tertiary carbon. We want to look for resonance as well. And now in this chapter, we're also taking a look at aromaticity, which could make something even more stable. So if we look at A, we can see that we have a secondary cation. And it does have some resonance stabilization. It is allylic to two of these pi bonds. So we can also say that it's a secondary cation, but is also allylic. If we look at B, we don't have any resonance stabilization, but it's still a relatively stable cation. It's a tertiary cation. If we look at C, this is a lot like A, where it's a secondary allylic cation. And every atom of this ring is sp2 hybridized. We do have an uninterrupted cloud of pi electrons, so we could check this for aromaticity. And what we'll see is that we have two pairs of pi electrons. So this is not aromatic. This is actually an example of an anti-aromatic compound, but we're not going to go into explaining that. The reason why we didn't check A for aromaticity is because we have an sp3 hybridized carbon that does interrupt that pi system. So that wasn't an option for aromaticity because we need to have that uninterrupted cyclic cloud of pi electrons. All right, and so if we look at D, we have, again, a cation where we've got some resonance. Every atom of this ring is sp2 hybridized, so we should check this one for aromaticity by counting the pairs of pi electrons. And we see we have 1, 2, 3 pairs of pi electrons. So this cation is actually aromatic because we have 3 pairs of pi electrons. And we're looking for an odd number, and 3 is an odd number. So this aromatic cation is going to be even more stable than the tertiary cation or that secondary allylic cation.